So now we're going to start talking about solving radical equations that contain two different radicals. And remember, if it contains two radicals, we are only dealing with when it has two square roots. A lot of these steps will apply just fine. If they're not square roots, it's just that the problems become quite a bit more complicated. So if there's two radicals in your equation, then we're dealing with two square roots only. So I'm going to give you the steps and I'm going to walk through an example while doing those steps so you see exactly what I mean at each step along the way. So here are the steps for solving. With the example, I will do number 7 on your handout, your 6.6b handout. So with example, so that example for the equation that we're working with, we're trying to solve the equation the square root of 4x minus 3 is equal to 2 plus the square root of 2x minus 5. That is the equation we're trying to solve here. These types of equations can be, in general, a bit more tedious than when there's only one radical. So just be ready for some complications to pop up. So the first step is we want to isolate, if it's not already done for us, we want to isolate one of the radicals. In this case, we are already in that situation. We see on the left-hand side here, one of the radicals is already isolated, that square root of 4x minus 3. So there's no need to do this step. If needed, you may have to add or subtract a radical or a number from both sides to be in this situation. So for this example, this is already done for us. Step 2 is to raise both sides to the appropriate power, just like we did in the previous section. But since we're only dealing with square roots, that appropriate power is always going to be squaring. So the only type of thing we're going to have to worry about is we're going to square both sides. And you have to be very careful during this step because it often involves the distribution or foiling of some more complicated expressions. So we want to square both sides and fully simplify. So for this problem, this is going to take a few different steps. Okay, so I have the square root of 4x minus 3 is equal to 2 plus the square root of 2x minus 5. And I'm squaring both sides. The left-hand side simplifies pretty simply. The square and the square root will just cancel each other. So I'll end up with 4x minus 3. The right-hand side, that's another story. So let's carefully multiply that out. Remember, we can't distribute exponents to terms. We have to multiply that binomial out. So I'm going to go over here to do that on the side, just so that my equation solving remains nice and neat. So I'm going to multiply this out. I have to multiply the 2 times both of those terms. So that will give 4 plus 2 square roots of 2x minus 5. Then I have to multiply this square root into the 2 and the square root of 2x minus 5. So I'll end up with another 2 square roots of 2x minus 5. Then that last term, since I'm multiplying the square root times itself, and this is what's going to happen for a lot of the problems, you're multiplying the same square root times itself, so you're actually squaring it. So take a lot of care here in making sure you're multiplying this out correctly. My two middle terms I can combine. They are like radical expressions. So I can combine them into a 4 square roots of 2x minus 5. And then that last term, when you're squaring the square root, you'll be left with just what's underneath. We can see there's a couple more terms we can combine. We can combine that -5 and that 4. So this will be a -1 plus 4 square roots of 2x minus 5 plus 2x. So squaring out that right-hand side was kind of a chore, but we made it. And that is what the right-hand side is after squaring. Looks quite different from what it was in the previous line, right? So that's step 2. Square both sides and fully simplify. Step 3, just looking at what we did, it doesn't look like it got any simpler, but it actually did. It got less complicated. Because what we did is we transformed an equation that contained 2 radicals into an equation that just contains 1 radical. So now I can apply the concepts from the earlier section for when there's 1 radical. So in step 3, if a radical remains, we want to isolate it, just like we would do in part A of this section. In other words, go back to step 1. From there, you would then, again, square both sides, fully simplify, and you'll typically only have to go through that cycle 2 times, maybe even only 1 time. But if your equation has a lot of radicals in it, you can expect to go through this cycle several times. But for us, the most we're gonna see is going through this twice. So if a radical remains, we want to isolate it, and in other words, go back to step 1. So looking at what we had previously, a radical does remain. So let me recopy what we have. I want to isolate this radical. So to do that, I'm going to subtract the 2x, and I'm going to add the 1 on both sides. Both sides. This leaves me with 4 times the square root of 2x minus 5 on the right-hand side is equal to 2x minus 2. Now the following is an optional step. I'm not going to make it, a requirement. But if you happen to notice that you can simplify both sides by dividing by some number, in this case, if I were to divide both sides by 2, the equation does simplify quite a bit. Okay, I'm not going to do that step here because in general you will not be able to do it, but try it yourself. If you were to divide both sides by 2, this 4 would become a 2, and this coefficient and this constant would become a 1, and it does simplify the problem a bit. But I'm not going to assume we're in that situation, and it's not going to matter too much. The only difference is by not doing this, we're going to end up with some larger numbers. So if in step 3, if a radical remains after simplifying, isolate it again, and you're going to go back to step 2, and then you're going to square it again. So now I'm going to square both sides. If I square the right-hand side, I will end up with 4x squared minus 8x plus 4. If I square the right-hand side, I will end up with 16 times 2x minus 5. For the left-hand side, I use the formula for squaring a binomial like I did in the previous video. For the right-hand side, I use the technique of squaring each factor separately and writing them here. So at this stage, there's no more radical. So in step 4, this is when step 4 comes in. If there's no more radical, then you are going to solve directly or indirectly for the variable using previous techniques. So in this case, I have 4x squared minus 8x plus 4 is equal to 16 times 2x minus 5. Let me just remark again that in the step that I'm about to draw an arrow to right now, if I had divided both sides by 2 at this point, this equation would look a lot simpler than it does. The only difference is the numbers are a bit larger than they have to be. So to solve this equation, I'm going to distribute that 16 in. I'm going to solve for x by bringing everything over to one side. And then, so in other words, setting it equal to 0, and then solving for x with factoring. So I'm going to subtract that 32x, that 80 to both sides, giving me a 0 on the right-hand side, and a 4x squared minus 40x plus 84 is equal to 0. So if you had divided both sides of that equation by 2, we're going to end up with an equivalent equation here, just with smaller coefficients. The difference is here I can factor out a 4. The first step in solving by factoring is the GCF. And then we continue factoring. Hopefully, I haven't made a mistake yet. So I want two numbers that multiply. And again, pause the video, maybe try to figure out how to factor this. I want two numbers that multiply to positive 24 and add to negative 10. If this works out, you probably didn't make any big mistakes. So this factors as x minus 6, x minus 4. And we set each of those factors equal to 0. And we'll get x is equal to 6, x is equal to 4. So let's go through this one more time. What have we done so far? We isolated one of the radicals that was already done for us. We squared both sides and fully simplified. That was this mess over here. If a radical remains, we have to isolate it and then square both sides again. So in this case, I had to isolate that radical that remained, and then I had to square both sides again until there was no more radical remaining. So in step 4, if there are no more radicals, we solve either directly for the variable, it could be a linear equation, or we might have to utilize factoring as in this case. The final step, just like in the previous part, we have to check. Since there's two potential solutions here, I have to check both. So I'm going to recopy the original equation. Which was this. Then I'm going to replace x by what I found. If you simplify the left-hand side, you'll have the square root of 21 . Oops. So it seems that I made a minor mistake looking at this back here. This is a lesson of what can go wrong, even if you know this material very well. When I factored out that 4, I screwed up at this point here. That should have been a 21, not a 24. So that means that the two numbers that I need, or the two factors I needed, were x minus 7 and x minus 3. Gives the solutions, or potential solutions, x is equal to 7 and x is equal to 3. I realized what went wrong. Normally when you're checking something, like an equation like this, you should end up with the square roots of perfect squares. So potentially not all the time, but that's usually an indicator that something went wrong. So I knew to go back and try to find my error. It took me a few seconds. So the video may have glitched a little bit, but I did find my error. So by putting in, I'm checking x is equal to 7 and x is equal to 3. So I will end up with, on the left-hand side, the square root of 28 minus 3 is the square root of 25. That's how I know that I screwed up somewhere, because almost all the time, even if it's a false solution, you will end up with the square root of a perfect square after simplifying each of your radicals at this step. So I'm wondering if this is the same thing. So the other side should be a 7 there too. This would be 14 plus 5. Oh, I even made another error there, copy error. That should have been a 2x minus 5. So this should have been 2 times 7 minus 5. And that'll end up with 2 plus the square root of 14 minus 5 is 9. So are those the same? Well, the square root of the left-hand side, that is 5. Is that the same thing as 2 plus 3? Yes, it is. 5 is equal to 5. So that means x equals 7. What I found after realizing my error is a valid solution. So this is true. Next, let's check x equals to 3. So recopy the original. So if I plug 3 in there, is that the same thing as the other side? Simplifying the left-hand side, I'll end up with 12 minus 3. That's 9, so I'll have the square root of 9 on this side. On the right-hand side, I'll have 2 plus the square root of 6 minus 5 is 1. The left-hand side simplifies to 3. The right hand simplifies to 2 plus 1. Are those the same? Yes. So for this particular example, there are 2 valid solutions. So my solution set is 7 and 3. Both are valid solutions. So those are the steps. You isolate a radical, you square both sides and simplify. If needed, you isolate another radical, square both sides and simplify, etc., until no radicals remain. Then you solve via factoring or directly, depending on what you end up with. So those are the steps, and we used example number 7 from the handout. So now we're just going to do the 2 remaining examples. I did modify one of the examples on the handout. This is the reason why I did not do number 6. Number 6, the modified number 6. This is changed from the original handout. It's very similar. And this one tends to be, you're going to see it's actually much simpler than the one we just did. So the one we're going to solve now is the square root of 2x minus 3 is equal to, 2x plus 3, that's what screwed me up, is equal to the square root of 5x minus 3. So I'm going to apply each of the steps. I'm not necessarily going to number them. We're just going to follow the algorithm. So the first step is to isolate a radical. As we can see, both sides are just a radical. So there's no radical that we have to isolate. It's already done for us. So what I'm going to do now is I'm going to square both sides. Canceling off the radical. In this case, it cancels off the radical immediately on both sides. So there's no need to do that big multiplication we did. And as we see after this step, no more radicals remain. So not only did I not have to do step 1, I do not also have to go back and isolate a second radical. So now I have to solve for our variable using techniques we previously know. So what I'm going to do is I'm going to move my variables over to one side and my numerical values over to the other. This is just equating 2 linear expressions. So I'm going to subtract. My choice is to bring my variables over to the left side. You may choose to move them over to the right side. That's fine too. If I'm moving my variables over to the left side, I'm moving my numerical values over to the opposite side. So on the left-hand side, I will have negative 3x. On the right-hand side, I'll have negative 6. Finally, I'm going to divide both sides by negative 3. And I'll have x is equal to 2. So we followed the steps and we got a potential solution. Now we just have to check. I'm checking x is equal to 2. Is it really a solution? Write down the original equation. Substitute what we found in for x. And simplify both sides. The left-hand side, I'll have the square root of 2 times 2 plus 3, that's 7. So I'll get the square root of 7 on the left-hand side. On the right-hand side, I'll have 5 times 2, which is 10 minus 3. So the square root of 10 minus 3 is the square root of 7. So I'm wondering if these are the same. And they are. I get the same thing on both sides. So in this example, we didn't end up with a perfectly simplified perfect square on both sides, but the square root of 7 certainly is the same as the square root of 7. So this equation is true. Sorry, this solution is a true solution. So here are my solution set. Is that valid solution x equals 2? Now let's look at number 8 on the handout. Number 8 on the handout is as follows. So I'm looking to solve this equation. The first step in this case is not done for us. I have to isolate a radical. It is your choice which radical you want to isolate. You can isolate the first square root of y, or you can isolate that second term, the 2 square root of y plus 1. I'm going to choose to isolate the 2 square root of y plus 1 because in my experience, isolating what is apparently the more complicated radical first tends to be a good strategy. Because when you're squaring that most complicated term, you're getting rid of that complicated radical right away. It does not matter what you choose to do though. If you wanted to try this problem by solving for the square root of y first, you absolutely may do that. Just check your answers at the end in line with mine. So I'm going to choose to isolate what I boxed in there. So to isolate that term, I'm going to subtract the square root of y and subtract the 3 from both sides. That will remove those 2 terms from the left-hand side. I'll have 2 times the square root of y plus 1 on the left-hand side. That'll be equal to negative square root of y minus 3. Some of you may already, if you think about it a bit, and I encourage that, you may already notice that this is not going to have any solutions. Think about why, and if you can't figure it out, you could ask during lecture. So we have isolated a radical, and what I want to do at that point is square both sides. If I square the left-hand side, just as we saw earlier, I have to square the coefficient and the radical portion separately. So I'm going to square the 2, and I'm going to square the square root. That will give me 4 times y plus 1. If I square the left-hand side, again, remember we have to multiply this out. You could actually remove the negatives if you know how. I'm going to assume that that is not known. So I'm just going to multiply this out the old-fashioned way. Multiplying this out, I will end up with a negative times a negative is a positive. So I'll end up with the square root of y times itself, which is the square root of y squared. If I multiply the outer, I'll end up with positive 3 square root of y, the inner positive 3 square root of y, and the last a positive 9. Simplifying this further, when I square the square root of y, I end up with y. When I square these two, I'll end up with 6 square root of y. Sorry, add those two, I'll end up with 6 square root of y plus 9. See how the negatives vanish there. Think about y also, if you're curious about it. So the right-hand side, I'll end up with y plus 6 square root of y plus 9. So what have we done so far? We isolated a radical, we squared both sides, and now we have to look at what we have after we simplified. A radical does remain. So I have to isolate that radical. Let me distribute this 4 over here first, maybe. So that 4y plus 1 is equal to y plus 6 square root of y plus 9. Now to isolate that radical, I'm going to subtract the 9 and subtract the y from both sides. On the left-hand side, I'll end up with 3y minus 8. On the right-hand side, I'll have what I wanted to isolate. At this step, once you have isolated your radical term, you might think, again, can I divide both sides by a number that might simplify both sides? In this case, that will not work out all that well unless you want to deal with some fractions. You will still end up with the correct answer if you do everything correctly, though. So at this step, once I've isolated that radical term, I'm going to square both sides once again to remove that last radical. On the left-hand side, I'll end up with 9y squared minus 48y plus 64. On the right-hand side, I'll end up with 36y. Once again, this is going to turn into a factoring problem, just like example 7. So I'm going to subtract that 36y from both sides, making it 0. And now we'll have 9y squared minus 84y, I believe, plus 64. This does not look like it's going to be really fun to factor, but let's give it our best try. So let's think. Can this factor as? So in general, I would use the AC method for this. There is no GCF, right? 9 only has the factors 3 and 3. 64 is not divisible by 3, so the GCF here is 1. So using the AC method would be a little bit painful, but maybe pause it, give it a try, see if you can figure out what to multiply to give you this. So it turns out, I apologize, this does not factor. We already know it doesn't have any solutions. So each of the potential solutions we find, they're actually not going to work out. At least, well, that was a lot of effort for nothing, right? So let me just show you one example that does work out. You can solve this with the quadratic formula, no problem. And it's just the problem of checking those answers in the original. It'll be a bit too tedious for what we expect in this course. So don't worry about that. So this will have two irrational solutions, just for your own knowledge, which don't work. This is far beyond the difficulty of what I'd expect out of Math 102. So let me just make sure, be careful, and copy an example exactly from your textbook. So here's something that you can replace, and I'll update the handout if you haven't watched. If you haven't printed out the handout yet, I'll change those questions. So new number 8, I'll call it. So let's look at something that has similar properties that this one had originally. Here's one. This is number 38 from your text. This is the square root of y plus 5, y plus 15. Copy errors, careful. Square root of 2y plus 7 is equal to 1. And the book is telling me this does have some solution. All right, so let's follow those steps again. The first step is to isolate one of the radicals. Your choice which? I prefer the more complicated one. So I'm going to isolate that radical. So to do that, I'm going to subtract the square root of y plus 15 from both sides. Leave me with, don't forget that minus sign that's out front there. It may have been easier to just add that radical to both sides. That's really up to you what you choose to do. Try it that way if you prefer. So I'll end up here. Once you have a radical term isolated, if you do not like that minus sign out front, you can multiply both sides by a -1. I'm not going to worry about that, but again, that's your option. At this step, I'm going to square both sides. And watch those copy errors. Today's not my day. So if I square the left-hand side, the first thing you should notice is if you square a negative, that -1 that's out front, the result is a +1. So the negative goes away. So really that square and that square root are really just going to be canceling. And I'll end up with 2y plus 7. On the right-hand side, we have to do what we did before. Very carefully multiply this out. So if I multiply everything out here, I'll have 1 minus the square root of y plus 15 minus another square root of y plus 15, and then plus that negative times the negative ends up with the square root of y plus 15 squared. Simplifying this, I can combine those two middle terms together. -2 square root of y plus 15. And here, the square and the square root will cancel. We're still not done simplifying. And these problems take a little while. I'll end up with 16 minus 2 square roots of y plus 15 plus that y here. So after squaring the right-hand side and simplifying completely, we'll end up with this expression. On the right-hand side. So just like the previous example, which was kind of botched, this has a radical that remains, so I'm going to solve for that radical, which means I want to get rid of the 16 and the positive y from this side, so I'm going to subtract the 16 and subtract the y. If I do that, on the left-hand side, I'll be left with that -2 square root of y plus 15. On the left-hand side, I'll have that y, and 7 minus 16 minus 9. At this point, if you saw it might be beneficial to divide both sides by 2 or -2, you could do that. But if I do that, I notice the left-hand side won't simplify if I divide by 2. So I'm not going to bother. So at this point, I'm going to square both sides. On the left-hand side, I'll end up with y squared minus 18y plus 81. On the right-hand side, remember we square the coefficient and the radical separately. So if I square the -2, I'll end up with a +4. If I square the y plus 15, the square root of y plus 15, I'll end up with y plus 15. Now I'm going to distribute that -4 in. It's frustrating. If I did make a mistake somewhere, you're probably screaming at me from 3 lines ago. That's just what happens with videos, nature of videos. So if I did make a mistake, I'll go back and try to find it. Remember, we're setting this equal to 0. Left-hand side then, the right-hand side I'll have 0 because I moved those terms over. On the left-hand side, I'll have y squared minus 22y plus 21. And thankfully, this does factor. If it didn't, like the previous example, you saw how nasty that was. I had a feeling something had gone horribly wrong, and it was with the problem. Um, it was miscopied from the textbook. So if you factor this, you'll find -1 and -21 are the two numbers that multiply to +21 and add to -22. So if you solve these two, you'll end up with y is equal to 1, y is equal to 21. So you can see in this section, the problems do end up being quite a bit longer. So now let's check. I'm going to check each of these. Y is equal to 1, and y is equal to positive 21. Rewrite the original equation way up here. This one as well. Let's see which one, if either of them, end up being true. So I'm going to replace on the left-hand side here y with 1. I'll end up with the square root of 16 minus the square root of 9, which ends up being 4 minus 3, equal signs. And I'll end up with 1 is equal to 1. So y equals 1 works. True. The right-hand side here, I'm going to substitute 21 in. So here I'll end up with the square root of 36. Here I'll end up with 42 plus 7, that's 49. Square root of 49. Question marks above the equal signs. This becomes 6 minus 7. Is that equal to 1? Well, 6 minus 7, that's definitely not 1. It's -1. So this is false. So y is equal to 21 was a false solution. Y is equal to 1 was a true solution, which means my solution set was 1. So again, as far as the real number 8 on the handout, and I made two. I miscopied the question number 8 from the textbook, and also number 6. I thought that would just work, and it didn't. So I had to change a sign in there for it to work out. So hopefully this example served its purpose to replace number 8 from the handout, which I will change right now. So come to class with questions, and I will end the meeting now.